is numerical number 3 today. It is today's last numerical. In this numerical, a spring mass system is attached in a somewhat different manner. Let us see that these are the two balls over here. You can view it very well. A spring has been attached with the thread of a mass system. This is a thread mass system. The thread is there, or a string, you can call it as a string also. With the help of a string, a mass has been suspended from this end, and again a spring has been attached to this string over here at this point. If I pull this mass like this through an angle of theta and keep my hand aside like that, I leave it, the system will vibrate in this direction like that. So due to the movement of this mass in this direction, that is theta, the spring get displaced. Spring also get displaced. So how much it is displaced? Since from here to here, this is your A. So if this is something like that, if I need to calculate it, if this is theta and this is your A, obviously this will be equal to your A into theta. So the displacement in this spring will be equal to A into theta. Next point, the storing force offered by the spring will be equal to K into displacement in the spring, and displacement in the spring is A into theta. Obviously in the opposite direction to the motion. The direction of the motion was on the right side. I had kept my hand on the ball and pulled it in a right direction to an angle of theta. Now, next point, since the ball is in a rotary motion and it is traveling an angle of theta, so an inertial force due to the D-Lambert force comes into the picture. That will be given by moment of inertia multiplied by the angular acceleration, that is I into theta double dot. This is an inertial force or inertial torque provided due to the D-Lambert principle, which will try to bring back the system to the equilibrium condition. Now point number 3, the third force into the picture. Since the ball is in this direction, so this is the dotted portion of the ball is the new position of the ball. The new position of the ball, we can analyze it in a mechanics manner. So mg is acting downward. So this is your mg cos theta and this is your mg sin theta. Mg sin theta is responsible for bringing the system back to the equilibrium due to gravity factor. So that due to gravity factor, mg sin theta, this is the force. Now, since all the terms are in the form of the torque, so we have to convert these forces also in terms of the torque, means the restoring torque. So this is the restoring force mg sin of theta multiplied by the mg sin of theta if I take it. So the total torque applied by this force, restoring torque will be applied by mg sin theta, will be mg sin theta multiplied by small l. This is the restoring torque applied by this mass due to gravity. Next point, the restoring torque due to the restoring force of the spring will be equal to Ka theta. This force multiplied by this perpendicular distance, that perpendicular distance is your A. So this is your restoring torque. I have written it and shown the direction also. So this will be in this direction. Obviously I have taken the ball in the anti-clockwise direction. So the restoring torque will be in the clockwise direction. So this is your clockwise direction. Ka theta, this is the restoring force by the spring multiplied by the perpendicular distance. So the whole term becomes as the restoring torque applied or offered by the spring. So let us analyze all these forces and have a solution out of it. So applying D-Lambert principle, it means the total inertial force plus total applied force, their summation must be equal to 0. So I into theta double dot, this is the inertial torque as per the D-Lambert principle, plus mg sin of theta into L. So this is the restoring force due to the gravity factor of mass m, which is suspended. Third point, so this is the restoring torque offered by the spring due to the displacement of A into theta. So we are again further solving it. So it can be written as bringing I in the downward direction. So I is coming downward, mg sine of, I have put in sine of theta as theta. I am taking as an assumption mg sine of theta must be equal to theta, as theta is very small. I have mentioned it also, assuming sine of theta equal to theta, as theta is very small. So mg sine mg, this becomes L, mgl upon I. Similarly, this is k a square upon I into theta. So I have combined all the quotients of theta in a single bracket. So I have equated as a number equation number 1. Now, but similarly, since it's a ball, it's a spherical ball, so I can be taken as ml square, and so the equation, put the value of I over here in equation 1. Similarly, I over here. By putting the value of ml square, I equal to ml square, so I got a relationship, another step number 5. Theta double dot plus G upon L plus K a square ml square into theta equal to 0. Again, I can compare it with the fundamental SHM equation that you know very well how to compare. By comparing that, I want to know that omega n square, this omega n square is known as the natural circular frequency. So this is equal to this much. Again, omega n can be calculated from step number 7. And from step number 8, the natural frequency of the system will be given as omega n equal to 2 pi. So put the value of omega n from step number 7. So putting the value of omega n from step number 7, we can calculate the value of natural frequency from step number 8. Thank you.